We start now. Just to remind you what we started to do last week. We started to work on resist modeling. We defined the photoactive concentration, and its normalized value is M. M is the amount of the photoactive compound. D is the exposure energy. D is also the dose, its intensity times the time of the exposure. And M is function of the dose, which is the multiplication of the power and the time. Dose is energy. It's energy per centimeter square. And energy per centimeter square is practically the number of photons per centimeter square, because we illuminate at a fixed wavelength. We illuminate at a fixed wavelength, and the wavelength is lambda. So the energy of the H photon is hν, or hc over lambda. So if the energy is fixed for every photon, the definition or the meaning of the dose is energy per centimeter square, but it's actually also the number of photons per centimeter square. That's why the M, which is the amount of how many molecules left in the material, the number of molecules which are affected is proportional to the number of photons. It's not necessarily that each photon affects one molecule, but there is a proportion. More photons, more photoreaction. So this is the meaning why I'm saying that M is function of D. M is the amount of the molecules normalized, D is the energy. I defined last week two rate equations. One rate equation is the amount of M, the photoactive compound, normalized. Normalized means initially M equal 1. When I destroy all the molecules, the concentration of M versus time initially M equal 1. When I illuminate the material, I induce a photochemical reaction. So M is destroyed, and if I illuminate enough time, M reaches 0. So this is, I don't know the exact solution, but the solution should behave like this. It probably be exponential. Actually, it's not exactly exponential. You will see that it's a little bit constant, then it goes down more rapidly, because the function here, M, or the rate, if I'm here, time t, and this is M of t, and I ask myself, what is dm over dt? How many molecules are destroyed per unit time? So the number of molecules is proportional to the light intensity. But it's also proportional to the number of molecules, because if the probability for destruction of a molecule is constant, the more molecules I have, more are being destroyed. And this is a nonlinear equation. dm over dt is a constant times I over m. This constant is called a C. The second equation is very famous equation from physics. It's an equation that if I take a substrate and I illuminate it with light, and the light intensity, I plot the light intensity I as a function of x. Let's define inside as x. On the surface it's equal to some I0, and it's going down, it's dropping exponentially. Why? Because of absorption. And if I am in coordinate x and the intensity is I over x, then the rate of decay of the light intensity, di over dx, is equal to some constant alpha times I. The meaning of this equation, you can write it also as di, the amount absorbed. If I take a slice here, which is dx, the amount of light absorbed in this slice, do you see from that direction, is equal to minus alpha I dx. This is the meaning of this differential equation. It means the amount of light absorbed is some constant, function of the intensity, but also function of dx, which is the absorption depth. So this equation, if alpha was linear, if alpha was constant, if alpha is constant, what is the solution for this equation? Exponent. So if alpha is constant, the solution is e minus alpha x. The absorption is exponential. However, alpha is not constant, and this is not the solution. And the reason alpha is not constant, alpha, the absorption is a function of m. Because m is the amount of the molecules that absorb the light. But n is also a function of I. And since I is a function of x and time, m is also a function of x and time, and we get that alpha is also a function of x and, of space and time, and alpha is a function of m. The good news that normally you can express alpha as a linear combination of a, m plus b. So we can, you know that every function we can develop to a Taylor function. So you can take like the first order term. But it's actually very important to understand. It's possible that we can have other function of alpha, but the most common expression for alpha is alpha equal a, m plus b, when a and b are constant. This is why this model is called the A, B, C model. A and B are the functions describing the absorption coefficient, and from the previous slide, C is this constant. So this is called the ABC model. Now let's take this model and let's assume that we have intensity. This is the surface of this. Let's see, and I need to explain you this. This is it's a little bit crowded. It's a little bit crowded here, so let me explain what I'm showing you here. Let's assume that this is the silicon wafer. This is the silicon wafer. This here, the silicon wafer. I hope one of this will work. This is the silicon wafer. And on the wafer, we have a thin layer of the photoresist. This is the photoresist. And I shine a light on the photoresist, and the light intensity, I plot here the light intensity. This is the light intensity I. This dimension I call x. This dimension I call y. And the light intensity is this function. So in this dimension, this is the image that I get from the optics. After diffraction, this is I minimum, this is I maximum. And because of diffraction, we get the image quality is not so very high. So I take this is the function of the light intensity. It can be one line and can be periodic. Depends on the mask. Depends on the image. So if this is the photoresist, I illuminate the photoresist, and then I ask myself, what is the concentration of M inside the photoresist? Now let's forget about the silicon. Let's say I expand this axis, and all this is photoresist. This is the photoresist. All this is the photoresist. So here I have a lot of light. Here, I have some light here, and here there's a very small amount of light. So initially, over the volume over the volume of the photoresist, M initially M of X and Y all over the photoresist is equal to 1. So everywhere in the photoresist M is equal to 1. I'm now interested, let's say, on the photoresist, on the function of M. If I take a slice here of the photoresist at the distance x0, I'm interested in M x0 y t. And the reason is, if I have a certain quality of the image, I'm interested in the concentration of the photoactive compound inside the photoresist as a function of x, y, and time. Because this defines the latent image. This is not the image itself, this is the optical image. And M as a function of x, y, and t is the latent image. This is the image of the chemical image, because this defines the quality of the photoresist. Now let's do this experiment initially in our head. Let's do it without solving the equation. Here I have a lot of light. So here we destroy the photoactive compound more rapidly. So imagine that initially the concentration everywhere was 1, 1, 1, 1, 1. Here the concentration becomes 0.9. I have more light, and after I illuminate more time it becomes 0.8. Now because the concentration of the photoactive compound becomes smaller, what does it mean? It means that the photoresist becomes more transparent. It absorbs less light. So this area becomes more transparent. So the area below it, we start to decompose, we start to destroy the photoactive compound. And then what happens is this region, under the illuminated region, we have some positive feedback mechanism, because here we destroy the photoactive compound, the photoresist becomes more transparent. That's why we get more light here. That's why we get more. On the other hand, here we have no light, very little light. So here the photoresist is not transparent. So what happens is that after a while, we destroy in this region, we destroy most of the photoactive compound. And this is a very nonlinear effect. This is why usually you get inside the photoresist the chemical image with much better. Look at the slope here and look at the slope here. And I intentionally describe it this way. We increase the contrast. Now let's try to estimate it. This is concept. Let's try to estimate it. Let's try to calculate in this direction M at a certain distance. We still don't know which distance. M at the coordinate x0. x0 as a function of y at any given time t. Now, I cannot give you an analytical solution anytime because the equations are nonlinear. But let's assume in one case that we have a photoresist with constant absorption. Let's assume that we have a photoresist, that we average it, and we assume that C is constant. And we assume that M plus B is constant. Now, this cannot be true because M plus B is never constant. But in order to solve the equation, let's assume it's a constant. I'm a little bit cheating, but I want to explain to you a certain situation. I tell you, when we can assume M plus B is a constant when B is very large and A is very small. But this is a very typical characteristics of a bad photoresist. Actual life, it's not so. It's more complicated. So if we assume that this is this term is constant, we can find this. If the intensity inside the photoresist is constant, we can assume that M is decreasing exponentially. Why? Because if we go to this equation, if I is constant, then dm over dt is equal to constant times I. Now, And where else we can assume that the intensity is constant? We can assume the intensity is constant if the absorption alpha is small. When the photoresist does not absorb very much the light, then we can assume that there's very little absorption and the I is constant. But again, I'm giving you some hypothetical situation. In real life, it never happens. But why am I showing you this? Because to give you some insight. Because if I is constant, then m over t is E minus CIT. Note here that C times the dose. Now let's take the derivative of m now in the y direction. So I can take this equation and take the derivative dm over dy. Now, the derivative of an exponent is the function itself. So the derivative is m minus the internal derivative minus ct. However, I is independent in the vertical direction, but it's a function of y in the lateral dimension. So I have to take the derivative di over di. Di over dy, sorry. Now, minus ct from this equation is actually, I can write it as ln m over I. Take ln m, I got minus CIT, so ln m over I is minus CT, so I replace it. So here is written m ln m over I, di over dy. So see what happens. The contrast, the slope of this function of m in the lateral dimension is a function of m, but it's also a function of di over I over dy. But this is 1 over I is also the ln I over dy. So this is the most important conclusion of this lecture. The rest, what we are going to do is kind of derivative of this equation. The most important parameter in the optical image is not the value of the image, but the slope of the log of the image. Because the dm over dy, which defines the lateral variations in the photoactive compound, is a function of we call this function ILS, image log slope. It's such an important variable, so we give it a special name, image log slope. And we can see that the derivative of dm over dy is m ln m. By the way, m ln m is a function which has a maximum for m equal 0.37. And I want this function to be maximum. I want dm over dy to be as large as possible, because it means it has a very large transfer from m equal 1 to m equal 0. I have to remind you that if this is the optical image, m in this direction, when there is light it will be 1. Sorry, when it's dark it's equal to 1. And when there is light it's going to 0. So the function of m as a function of y is the opposite of the function of I as a function of y. And I would like this transition here to be as steep as possible. Because this is no exposure, exposure, no exposure, exposure. And this is the chemical image inside the material. So to conclude this long explanation, which took like 10 minutes, the contrast, the chemical contrast inside the photoresist is a function of the image log slope d ln I over dy. And it's the best contrast we get when m equal 0.2 to 0.5. So actually one conclusion is that we don't need to fully expose the photoresist. If we initially m equal 1 and we destroy it, when m become between 0.2 to 0.5 we get the best image. We don't really need to illuminate until we get m equal 0. So if you ever design your own lithography, and I see here a few graduate students and they usually design their own process. one of the questions that you ask, how long I will do the exposure? 1 second, 2 seconds, 3 seconds. So normally you say, oh, I will increase it as much as possible. No need. There's an optimum value. Because if you start to over-illuminate, what will happen here, at the minimum, you will start to accumulate exposure. And this value will start to go down. And then you will destroy the image. So too much exposure is not too much, it's not good, and too little exposure is too good. There is some optimum. So let's go on. So this was a complicated slide, and now we go to the result. The result is that, if you remember, we deal with a positive photoresist. In a positive photoresist, where we illuminate the photoresist, we remove it. It's removed. So here, this is a function of a normalized resist thickness. Initially, it's equal to 1. It's normalized. And this is the dose. E, exposure dose in energy. Typically, it's given in millijoule per centimeter square. Typical numbers are in normal photoresist. This X scale is typically given in millijoule per centimeter square. And typically, you plot this in a log scale, because the resist contrast depends on the log of the dose very strongly. And the typical function, it's nothing, 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 nothing. Then we destroy most of the resist, and at a certain threshold, we call this resist removal threshold, we eliminate so much of the photoactive compound so the resist becomes soluble. So we remove the resist. The slope of this curve, we call it the contrast, and this is the photoresist contrast. Don't confuse with the optical contrast. This is the second contrast that we learn. This is the photoresist contrast, and it's the slope of the curve when we plot the resist thickness as a function of the dose in a linear log scale. So gamma, or the resist contrast, is d ln of the resist thickness over d ln of the energy. By the way, you can take ln, you can take log, it will be the same. So in some papers you can see log, some papers you say ln, but you will get the same function. So we call this the resist contrast. So if I conclude, if I want to get good lithography, first ILS, the image log slope, is a good characteristic. There is a good correlation between the ILS and the line width and the image. The ILS is deteriorated by defocusing, which means but this is normal. If I go out of focus, I destroy the optical image, and instead of having a sharp image, I will get the transition between white and black is become more diffused. The development and the latent image is the image which is kind of asleep inside. This is the chemical image. The latent image variables depend on the resist material, development tools and process. The best way to optimize is to run exposure development matrix for the best focus. And the resist contrast depends on the exposure development matrix. What is the exposure development matrix? You are taking the wafer, exposed with a certain energy, and develop in a certain time. So usually when you take the wafer and you put it in a developer, for all the dyes on the wafer, you give the same time. So usually you run few wafers, and each wafer you expose in a different dose, and each wafer you develop for a different time. So you, at the end of the day, you get and you measure the results, and you can generate a matrix of a function of the exposure and development. Let me explain to you in a little bit more detail what does it mean. What do you measure? Let's say you take a wafer, and in this wafer you expose the dye. You can expose the dye in a certain energy, E1. Then you expose the next dye. E2. The next die, E3. So you can expose a whole row or certain places with a different energy, because you can control the time of the exposure. So you can control the dose. Each one is a different energy or D. It's for me it's the same. E or D, energy or dose, I refer to the same value. Once you expose it at a certain exposure, you dip it in a developer. And the developer removes the exposed resist. So you can take a shot of your wafers, and every wafer you develop in a different time. So what do you vary? E, dose is a variable. Development, time of development is variable. Then you can plot your result as a function of D and T, and you can imagine that you will get some two-dimensional function. Now what do you measure? Usually what you measure is, if you have lines and space, you measure line and space on the wafer. And you can plot like the pitch or the critical dimension, the line width or the space, basically any variable that you like. You can measure the slope of the photoresist, you can measure the line, the width of the photoresist. You can define what function that you like, and you can plot this function as a function of D and T development. As a rule of thumb, the more light, let's take a mask, and this mask is dark, and I illuminate, and this is the optics, and on the wafer I get here let's say 2 lines or 3 lines. Where I illuminate, I remove the photoresist. So where is dark, this is the wafer. I will get the photoresist here, I will get the photoresist here, I will get the photoresist here. If I will plot the light intensity, I, as a function of y, in this direction, here I will have light, here no light. Here I have light, here no light, here no light, here I have light. Now let's say I increase the dose. More light will reach the wafer. More light will reach the wafer. The line will, the photoresist will shrink, because the photoresist, there's more diffraction, there's more light being diffracted to the side of the lines, we get narrow lines. Also the same, if I increase D, I reduce the lines, increase the space between the lines. If I increase the development time, which means there's more time I put it in the developer is an etcher, it etches photoresist. So if I increase the time of development, I will also affect the line width. So I can play with the amount of energy, the amount of illumination, I can play with the developer. And I have some room. Now the question is, what is the best condition? The best condition is to answer the following problem. The following problem is that actual lithography is never ideal. And you can have variations in the process. You want the light intensity to be the same all the time, but it never happens. You can have variations in the light intensity. You have some fluctuations in the light intensity. You want the development to be exactly the same time, like 30 seconds, but it can be 29 and it can be 31. So you have variations. So the best lithography is to find the conditions, and it's a problem in the field of optimization and control, to find the best conditions where you have a process window, a wide process window, which means even if you change a little bit D, or change a little bit the development time, you still have the best possible results. And I'm going to show you some example how to do it. So we call this CD control. So what determines the lithography quality control? And we have the random variations during the process, and we have the response of the process to these variations. For example, let's say we have the following image. This is the dose versus position. This is space. This is line. This is space. Why this is a space? This is a space because here we have a lot of light. and we have a lot of light, we remove the photoresist in this area. So after we do the lithography, here we have a space. Here we have a line because we have very little light, so the photoactive compound is not destroyed, so the line stays. Now let's call this critical dose. If you remember, there is a critical dose that above this dose the photoresist is completely removed. Below this dose the photoresist stays. So if I plot this line here and took a line here, this will be the space, this will be the line. Now let's assume that this is if we have an ideal function. This is if we have if you remember, we plot the photoresist thickness and normalize between 0 to 1. This is the resist thickness, and this is the dose, and we have a critical dose, D critical. In some papers people also call it E0, or some papers people call it E critical, but this is the critical dose. Below this dose the photoresist stays, it's not removed. Above this dose it's removed. Now this is for a photoresist with what kind of contrast? Very high, infinite actually. So this is like an infinite contrast, which never happens, but in infinite contrast this will be the line width. This is the space, this is the line. But in real life actually we have here some slope. And we have an area between, we call this dose. You see D0 and D100. So this is the dose. When we have still 100, this is the D0, and this is D0, and this is D100. D0 means 0% removed. D100 means 100% removed. And this is linearizing the curve. In real life, the actual function looks even more complicated. But if I will linearize the curve, and typically the linearization is done when I plot resist thickness versus log D. It's very common to plot these curves in log scale, linear log scale. This is the convention in lithography. So we define the contrast in a lean log scale. So if I look at this curve, what happens here? Now, if this is D0, here we start to remove the resist. This is D100, because we remove all the resist. So the edge, now the edge of the resist is not infinitely thin. We have some transition between the bottom and the top of the photoresist. We have a slope. So the higher the contrast of the photoresist, the better the quality of the line. Now, like any practical questions, you have to ask yourself, what is a good contrast? 2, 3, 5, 1000? And second question is, what can I achieve with normal photoresist? Because I can think of a theoretical value, but in practice, we depend on the material properties. A good contrast typically are in the range of 2, 3 to 10. It's difficult to get higher contrast, but it's possible. So if we look again now in the situation, example of the quality of the aerial image, this is the optics. And this is a good image. This is I minimum, this is I maximum. I plot here this is the dose of the illumination versus the position. So this is a good image. And this is D0 and this is D100. And I intentionally took it from a paper where we have a relatively low contrast photoresist. This resist is low contrast. D0 here is like 0.3 and D100 is like 0.6. So we have the contrast, you can calculate, it's 1 over log of 2. It's about contrast of about 1.5, which is not so high. And this is the quality of the image. This is the quality of the image. This will be the transition of the photoresist. Now let's say we have a bad image. This image is, the maximum light intensity is lower because of diffraction. This will affect the quality of the light. If I will plot now the shape of the photoresist, or approximately, in the left image, if I plot here the resist profile as a function of x, the left line will probably look like this. The right line will probably look like this. The slope will be the transition between the bottom and the top. This is the resist profile. And this is an approximation. This is, of course, this is, I would say, this is a very rough approximation. We'll show you how to do better approximations. So, yes, questions?
Isn't it also depends on the intensity itself? You can play with the intensity.
No, it depends only on the dose, not on the intensity, until certain intensity. Of course, if I illuminate at extremely high intensity, I can destroy the photoresist. If you illuminate at very, very high intensity, it's possible to decompose the photoresist, generate nitrogen, you start to see bubbles in the photoresist, but this is not a good idea. There are some limits. It's a good question. Everything I'm telling you now is good within a certain regime of operation. If you take a photoresist and expose it with intensity which is too high, which is sometimes common if you use laser exposure, then it's a different ballgame. It's a different model. You reach saturation, you depend on the intensity, but it's not a good... There is some maximum allowed intensity which people usually use for normal photoresist. But usually it depends on the dose, not on the intensity.
If you increase the dose...
If I increase the dose, maximum will be more maximum. The minimum also will increase. Then I will get better slope. If I will increase more, it's possible to improve the result, but it's also I will increase the minimum. If the minimum will reach this value, then I'm in trouble. So I have an exposure window. And again, of course, if I increase the dose, I can increase the quality of the image. True. Now, now let's forget the complicated theory and let's ask the question. I defined a value which I call CD. CD is critical dimension. Critical dimension is something I can define. It can be the width of the photoresist on the gate, or the width of the contact, or the width of the line. Any value when I run a process, I can define as a critical dimension. Typically, the critical dimension is the dimension which is very, very critical to my process. In MOS process is typically the gate length. So let's say, normally the line width, this is the critical dimension, and this is the dose E, which I need to define the CD. If I will reduce the dose by 10%, for example, and if this line is linear, this will be the CD. So, if I will increase the intensity to a certain value, I can reduce the critical. If there is less light, the line width increases because there is less light in the exposed region. I can define like CD plus 10%, CD minus 10%. What does it mean? I can define it. It's a definition. I can say that I allow in my process to be plus minus 2%, plus minus 5%. This is an example of CD of plus minus 10%, which is pretty large. So once I define how much I can change in the process, it defines E. How much change in the illumination is allowed. So this is called the process latitude. How much I allow in the process to change in the light intensity or in the dose to allow a certain change in the critical dimension.
Could be the dose and not the intensity, because you have also the time.
No, this is a function of the dose, which is the time and the intensity.
Can you repeat the question?
Can you repeat the question? please?
No, you did.
Okay. What was the question?
I asked whether the E is the exposure or the dose.
E is the dose. E is the dose. Line width is a function of the dose. So I can illuminate in a larger intensity with a shorter time, or use a shorter intensity, lower intensity and longer time. And one trick that people can do is, while exposure, you measure the light intensity. And let's assume that you're using a lamp and your lamp is getting older, the light intensity is going down, so you can compensate. You can change the duration of the exposure as a function of your lamp intensity. And in many systems, in the past, people actually did it. They put a light meter and you design the dose, not the intensity. And the system automatically adjusts the dose. Now this is more complicated because the dose, the CD, the line width, is a function also, not only of the dose, it's also a function of the focus. The dose defines the line width, but also the defocus. Because if you go out of focus, you destroy the line width. So you can actually plot, let's say this is contours of a constant dose. And this is increasing the constant dose. And this is the line width versus focus. This is I apologize for the low quality, but what is written here is focus position, or the defocusing. So this can be like the best focus, this is a little bit too high, this is a little bit too low. And how it's been done in practice, you take the wafer, you expose it with this dose D1, D2, D3, D4, you expose the line, and this line in a certain focus, let's call it F1. Then you take the wafer and move it up a little bit, and repeat, and do all the exposure, D1, D2, D3. Then you move it up a little bit, and then you develop it. So you can actually develop and measure the line width. So you can actually plot the line width as a function of the energy and also a function of the dose. And there are a few ways to plot it, because it's a function of the line width is a function of the dose and the focus. Very difficult to plot it in a plane. So one way to do it is to plot it in these contours are the contours of constant energy. And what you see, very typical result, is you can have a certain defocus. So the focus can be here, 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 and here. In a certain energy, you find the lines here are flat. This is a very common solution to this problem, and we're a little bit lucky, but this is effect of life, that there is a certain distance in the defocus which gives us, it doesn't matter. The focus can be here, here, and here. The line width will be constant even we go out of focus. We call this the focus length, or the amount of defocus, and this is the practical defocus. It's not a theoretical defocusing based on Rayleigh's equation. This is the practical defocus from actual measurement on the wafer. And usually a good engineer will define the CD to be here. If you define the CD to be this CD, maybe it's too large. You want to make it smaller. But if you choose this dimension, you're extremely sensitive to the depth of focus. And we know that if we improve the resolution, we pay with depth of focus. So for this result, this is the best line width, and usually if you do it right, this will be your critical dimension. If you manage to get this result, then you are lucky, or you're a good engineer. And but it's much more complicated, because if you can also plot, this is another plot, and this is the focus. This line is the focus, and this is now the exposure energy. And I plot here contours of a fixed line width. So if I have three variables, the line width is a function of the energy of or the dose and the depth of focus, or the focus place, I can always choose one variable to plot as the other two variables. So in this plot, I choose for every energy and for every focus, there is one line width. So I can connect all the line widths which are the same. And this is one contour in this plot. So this is one line width, this is the second line width. And I can choose the best condition, for example, to be here. I want to be between, this is the CD range, and I would like to be in this region. So this is the process window. I allow myself to be, the focus depth can be between this region and this region. Oops, sorry. And the amount of energy can be, if you see this green light, to be around this region. You are going to exercise it in the class, you can do it the homework, but this is, I'm just showing you some of the problems of optimizing a resist process. Because it's a non-linear process, I would like to find the solutions where the process is most stable, where I can change the depth of focus, I can change the energy and still get the same result, or almost the same result. And I can calculate it. If I know the line width, I can estimate the performance of the transistors. And I can transfer it to the designers. I can tell them, your critical dimension is 45 nanometer plus minus such and such. And they can do it, they can take it into consideration when they model and when they design the circuits. So this is a very important very important feature.
What is the red line here?
Okay. Thank you for reminding me. There are a few other issues. This is the ideal place. This is, for example, the best result if I'm not taking into consideration other variables. Now there are other mechanisms that can be a problem. I can put also other constraints. Let's say this is the substrate, this is the substrate, and this is my photoresist. I got a beautiful process. This is the photoresist. I get another line, and it's a beautiful process. And I'm very happy with the result, and I got the CD that I want. But if you remember, microelectronics and nanoelectronics is not about getting good resist. I need this resist later to etch the substrate. So the next step is to etch the substrate. Also, during development, I'm running some sort of processes. I can heat the photoresist, I can clean it, there's some other processes. So during these processes, I can lose some of the photoresist. Simply, I dip it in etches, I dip it in cleaning solutions, I dip in acids or bases. I can lose some of the photoresist. Also during the etching process. So if I allow myself, for example, that the photoresist loss is not more than 10%. The photoresist loss, for example, depends on the slope of the line. Because in many processes, and when I teach you about etching, the loss on the sides depend on the slope because we apply some energy from the outside. So if I limiting myself that I want during this process, I cannot lose more than 10% of the resist, I will have to be within, for example, this region. And then there is another constraint. For example, it's called slope of the sidewalls. If I will, if I get ideal results, and I change the focus, I change the slopes. And in many cases, you can say that you design the process and you allow yourself the slope to be between 90 to 85 or 80 to 90 degrees. So if you limit the slopes of the photoresist, you define these blue lines. So you can define on this energy versus focus And this is the critical dimension, and this is your best critical dimension here. You can also define other constraints, like resist loss, how much I allow myself to lose, how much resist I can lose during the process, or what are the sidewalls. And there are some other possibilities. But constraints. If I summarize this lecture, it's going as follows. In a normal lithography process, your line width depends on the dose, which is defined as the intensity times time. And the dose is the most important function. However, also the focus also is a problem, because you want to be in the best focus, because if you're not in focus, your image becomes with less quality. So the dose and the focus are the two variables, and you can define your critical dimension as a function of the dose and the focus. And you are looking which you can assume that you can have some variations in the CD, and this is your process latitude. And this process latitude can define some variations in D and the variations in the focus. Now, variation in the focus is a bit of a problem, because sometimes you cannot control it, because if this is your wafer and you have some line going like this, during the process you will have the image here and here will be a little bit, there's some focus variations because of the process itself. So it's sometimes very difficult to avoid to be out of focus. You have some defocus because of the shape of your wafer. And this, how much you allow, it's called the depth of focus. And you want to get the best resolution within a certain distance of certain variations of the focus. And we all summarize in this graph, and you plot usually, you can, by the way, you can generate it in theoretically. If you have a good simulator, and we have a good simulator, we can run and generate exposure or dose exposure or exposure focus matrices, and actually simulate everything and even get results before the experiments. And then we run the experiments in the lab. Now, run it in the lab is expensive and can take some time. So what you're going to do in your homeworks is simulating it and learn how to use the simulator. And this is an excellent simulator, which is very close to reality. And what you're going to do this week, this week and next week and the week after, you're going to run a lot of experiments in lithography, but by simulations, which is actually very nice and save us a lot of money. So, and it's a commercial simulator. It's a ProLith, which is a commercial simulator, which are, as far as I know, most of the companies are using it. So you will get some hand-on experience. And the GUI is fantastic. So you don't need to know the software. The GUI is very, very, I mean, you are overqualified for using the GUI. It's very simple GUI, and the teaching assistant will teach you how to use it, and it's very user-friendly. And it's now 6 and 5 minutes, and we're going for a 10 minutes break. The last lecture was with a lot of equations, but I would like to stress one point. Why photolithography is such a successful technology. I would like to bring to your attention the following. Let's say we have a photoresist. This is a photoresist. And here I have light. There is some light here. I would like you to think about the effect of the photoresist. In this area we have light. Because we have light here, this area we destroy the absorption component. So this area becomes transparent. So this area becomes transparent. So we expose the area below it. So every area which we expose becomes transparent. Then we expose the volume below it, and we expose the volume below it. So eventually this area M is equal to 1. Here M is much smaller than 1. So you can think about it as an optical drilling. It's a mechanism where you illuminate, the illumination becomes more effective. Here it's dark, so nothing happens. However, this is not so correct because we have diffraction. The wavefront actually propagates on the side, so this transition between 1 to 0 has some volume. Now, in order to calculate it completely, you need to solve the wave equation in 2 dimensions and to solve everything in 2 dimensions, but this is beyond the scope of this class. But I would like to think about the principle that optical lithography has some drilling effect, and this is why the image inside the resist is of much better quality than the optical image on top of it. Questions? No, it's not so. The question was, is this good also for negative photoresist? The answer is not so much. This is why positive photoresists are much more desirable. So now the next question, the next lecture is, and I promise not so many equations, actually not so equations. Now sit back and relax. I'm going to tell you how do we measure. Let's say you design your photoresist, you have a wonderful lithography. Now I ask you, what is the line width? How do you measure the line width? There are 3 common methods. One is CD-SEM. CD is critical dimension. SEM is scattering or secondary electron microscope. The most common method today to measure photoresist is CD-SEM. One of the common methods. Second method is to use AFM, atomic force microscopy, which gives very nice results, but is not so fast. It has some problems with speed, but it's also a method we can use. And the last one is optical near field, and I'm going to show you a little bit more of optical CD. So what is basic elements of a CD scanning electrical microscope? We have a field emission. We generate a beam of electrons. The beam of electrons is going through the system. Here we have a set of kind of a lens. So in the end, the beam goes and hits the substrate. The beam hits the substrate. The electron hits the substrate. We generate secondary electrons and we collect them. So we can, if we scan with the beam of the electron, we can generate an image. So this is a scanning electron microscope. And the nice feature of the scanning electron microscope is that we can generate a very, very thin beam, very narrow beam of electrons. So it's like taking a pencil and kind of drawing or plotting a line on the substrate, but instead of using a pencil, you're using a very sharp pencil. So this pencil is made of electrons. So if you look at, this is a photoresist. The black is a cross section of the photoresist, and this is how it looks from the top, and this is how it looks from the side. And you are generating electrons by taking a beam of electrons, and they hit the photoresist. You have many of the electrons hit the photoresist and going inside, but some of them are backscattered. So we have backscattered electrons, and some of them are secondary electrons. The electrons hit the substrate. They are so energetic, they break some of the bonds, and some of the secondary electrons are emitted outside. So this is the primary beam of electrons, and those are the secondary electrons or the backscattered electrons. The beam can hit the top of the photoresist, the beam can hit the side of the photoresist, the beam can hit the bottom of the photoresist. So if I measure the secondary electrons, I will get some signal from here, some signal from here, and some signal from here. So what you usually do, you scan with the beam from the left to the right, for example, here. And then you measure the signal. This is like this signal, and this is a signal, this signal, and this signal. So what you're actually doing, you're put here a detector, somewhere here. The detector can be here or here or here. And you're collecting the secondary electrons. And you measure it. You actually measure current. And when you move the electron beam along the line, you measure how many electrons are coming out of the sample, and you have the intensity as a function of distance looks like this, and from this you can extract or estimate the line width. It's a very good method, but it's a little bit problematic because you need to know a little bit about the shape of your lines in order, if you measure, this is the electrical signal. This, you see the white line here? This is the electrical signal. Here you collect a lot of electrons, very small number of electrons. A lot of electrons, small number of electrons. So you have here you have one type of material, here a second type of material. Or what I forgot to tell you, that the amount of secondary electrons depends on the type of the material. So if you illuminate silicon with electrons, you generate X number of secondaries. If you illuminate photoresist, you're generating Y electrons. So you have a different signal, depends on the material. But the amount of secondaries depends also on the shape of the photoresist, because here you hit the photoresist in perpendicularly, and here the electrons is traveling and is hitting in an angle, and typically when you hit in an angle, you generate more secondary electrons, because it's like if you're throwing a stone on the water, you have longer interaction near the surface. And you can generate more electrons which are coming out. Yes?
Isn't changing the charge of the material?
Now we can have problems. We can charge the photoresist. And if we charge the photoresist, let's say electrons are coming, charging the photoresist, then the next electrons will be repelled. So we have to somehow design a mechanism to overcome this problem. I'm not going too much to detail, but it's possible. This class is only about, I don't want to go too much into the physics, but there are certain energy, there's certain energy that for every electron coming in, there's one electron coming out, then you don't charge it. So you can play with the energy of the primary electrons and play with the charging. And you can do some other tricks, but the problem of charging is a very big problem in this technique. Now, let's go a little bit, let's describe a little bit the physics behind it. This is your specimen. You hit it with the beam, and there are electrons coming out. The electrons coming out, actually, you can also, there's some X-ray coming out, because if electron hits the substrate, there is some interaction. And you can have also a cathodoluminescence, some visible light coming out. And if you connect this to ground and connect this to amplifier, and if you're an electrical engineer, you know that you can measure the total current coming out. So you can actually measure how much current, how much current coming in, how much coming out. You can estimate this value of this current, and this is the specimen current, and you can measure you can either measure the current here or the charging current, or another alternative which is more sensitive, to put here a sensor or an element that collects the scattered electrons. So this is the few modes of SEM. You can measure the emitted electrons, you can actually measure the X-ray, or measure the cathodoluminescence. The most popular SEM actually you are collecting the emitted electron. This is the most sensitive way. So let's again tell you what the electron beam parameters related to CD measurements precision. This is your substrate, and I apologize for I took this from papers, and the quality of the images sometimes is not so brilliant, but you can look at the value. This is your electron beam. You move it from here to here to here to here. Here you suddenly hit the photoresist. You hit the photoresist, and let's say this is a material which emits more electrons. So suddenly you get increase in the number of electrons. You reach the top of the photoresist, but here you hit in an angle, here you hit in perpendicularly. Typically on the side walls we get more secondary electrons. So this will be your signal. You have to decide, where is the line width? Is it here? Is it here? Is it here? You also have to take into consideration that the beam itself has some width. Another problem is that all the models, or the initial model, we assume that my wafer is perpendicular. But what happens if there is some tilt? It can be a problem. Another issue is that if the beam itself has some width, so the actual image is a convolution between the shape of the beam or the width of the beam and the width of the photoresist. So some problems. And this is actually the issue of spatial resolution. This is, let's say we have, if we have two images which are too close, we can get a SEM signal which look like this. I went to a few papers describing actual images, and this is some very, very, I would say, it's a kind of interesting situation that when this is the signal, this is the intensity or counts of the electrons. This is the side of the beam, this is the edge of the line, and this kind of material, it's actually on the top we get much less electrons. So if you are looking at the collection of electrons from a beam, it's possible that you can get this image, the intensity of the electron, of the scattered electron as a function of distance, can be like this. And the photoresist, actually, this will be the photoresist. It depends, in this specific one I didn't say which kind of photoresist, but let's say we have the photoresist that look like this. And we got here certain emission, here certain emission, here certain emission, but on the sides of the photoresist we get much better scattering because here the electrons are emitting a lot of secondaries. So one of the issues of using electron beam to measure line width, this is actually much more sensitive to the sides of the image than the actual image itself. So you need to think of an algorithm. This is the intensity to define where is the edge. Is the edge here, here, and here? So what people actually do, they take the measurement in the SEM, cross-section the wafer, actually measure the line width and correlate between the electron beam image and the actual image, and you generate kind of a lookup table to define. But the definition here is not trivial. So how do you calibrate? So one of the problems is how to calibrate the SEM. You measure a certain image on the SEM, but the image depends on the sidewalls. So one very common option is to calibrate with AFM. AFM is a tool that you take a very sharp tip, you put it next to the wafer, and you measure the force between the actual force, and you move the tip. And actually, if you can operate in a constant force or in a tapping mode, you can actually measure the topography of the structure. You can move it, you reach a higher area, you move it up or move it down. So by moving the AFM, you can actually measure this. This is a very nice photoresist lithography, and I took this image. This is a very advanced lithography. This line width was in the range of about 100 nanometers, and this is kind of very ugly photoresist. And it took me a little while to find in the literature a picture of a bad photoresist, because all the publications, they always put good photoresist. But I found this paper. This is the image of the photoresist. This is how it looks. This is actual cross-section of the photoresist. And what people usually do, measure the line widths by SEM, then measure the line width by AFM, and then you plot line width versus line width of SEM versus line width of AFM. Draw a straight line and use it as a calibration line. Why do you do this? Why do you need this? Because normally you don't measure a single line. Because every day you have hundreds of wafers, and every wafer you need to generate the data. So you scan them with the SCM, generate the data, and then you can plot, for example, line width versus time. This is like an image that you get from an AFM, and this is the image you get from the SCM. And this is another image from the AFM. This is the image you generate by the SCM. The AFM is more accurate because the tip is very sharp and you can generate a very nice image. The SCM, you see, this is the image of the SCM. You can see this is the photoresist. This is the photoresist. This is the valley between them. But you can see that the transition between the black here and the black here, there is some white area which is a little bit undefined. It's an error. So you need to calibrate it. So the conclusion from these images that even SCM, which is a very accurate method, because of the slope of the lines, there's some uncertainty, so we need to calibrate it.
Is it an error or actually the slope of the line?
It's a good question. The question is it an error or just what I would call a bias, like a constant fixed error? Because if the error is random, I have a problem. But if it's kind of a fixed shift in the value, I can calibrate it. The question is, it's a strong function of the slope of the line, but I can calibrate it because it's for every slope, it's a fixed value. So if I can estimate the slope and I have the AFM values, I can correct the SCM values. But the point that you mentioned is very important. SCM, or the quality of the measurement by SCM, depends on the algorithm and depends on also some accumulated knowledge in the company. And my conclusion is that, or my advice to you, that even if you use automatic system and you buy them and you pay a lot of money, think before you use the results, because sometimes there are few possible algorithms. You have to make your choice. So this is CDSM resolution. Typical numbers for CDSM is 1 to 5 nanometers. CD metrology on resist is 5 to 10 nanometer precision. Now, this sounds like very impressive values, 5 to 10 nanometers. Wow. However, if you work with a 32 nanometer technology, 5 nanometer error is not so good. So, in the good old days, which mean like 2 years ago or 3 years ago, when people worked with 90 nanometer, then 5 nanometer error is not so bad. But in the next future, when you work with 32 nanometer technology, even electron microscopy needs some improvement, or finding an alternative method. What are the methods? For example, some atomic resolution. And the problem is actually you have to go backwards. What is a CD? What does it mean? Because if you look at the line width of the photoresist, this is your photoresist. If you look at 32 nanometer line, it looks like this. It's not so nice anymore. If you look, this is the photoresist. Here there was no light. Here there was a lot of light, so we removed the photoresist. So this is like the line width. Look at the edge of the photoresist. And this is actual image. When I actually took it from a real photoresist, we call this line edge roughness. The sidewall of the photoresist is actually, if you go to very, very high resolution, if you go to nanolithography, this is 32 nanometer, but if some of you working on nanolithography, which is like 10 nanometer or 5 nanometers, then you find out that your sidewalls are not so smooth anymore because of a lot of problems. For example, one of the issues is that because the volume is so small, the number of photons that reaching the substrate is also it's a very small absolute value of photons. So you have, and this problem of line edge roughness is a very big problem, because first, if you have this roughness, how do you define the CD? Is it on the narrow line or the wide lines? Second, people found out that this line edge roughness, you transfer them to the substrate when you do the etching. And if you define a metal line, how do you define a metal line? The way to define a metal line is the following. You take your substrate, you deposit metal. This is metal. On this metal you put a photoresist. This is your photoresist. PR. Then the next step, you etch the metal. Let's assume if this is aluminum, very typical way to etch aluminum is to put it in a plasma of chlorine ions. The chlorine ions go and etch the aluminum. So you remove the aluminum. Actually, during the process of the etching, you can have some photoresist erosion because of this chlorine ion is a very corrosive gas. You also can affect a little bit your photoresist, so at the end of the process, it looks a little bit different than the beginning of the process. But even worse, this is a 2D plot. In actual life, we have a 3-dimensional line. So I define here an aluminum line at the end of the process I will have aluminum lines, but the aluminum lines can be a little bit rough on the sides. People found out that this roughness affects the reliability of the metallization. Because what you do with metal lines, you put current into them. This is current. Current is flowing into the lines. And the current density is very high, especially because we work with very narrow lines. And at very high current density, we have an effect which is called electromigration. The electrons actually can move matter, and you can generate voids here. And there's a very strong correlation between the quality of the lithography and the reliability of the lines. I will not go into detail. This is something which has been investigated in the last few years. It's not fully understood. But there's a very strong correlation between the quality of lithography and the quality of the reliability of the lines. You can think about it. If the line is very smooth, there is less defect. If it's not so smooth, you can have corners and some structures, but this is a material for another class. Yes, questions?
What is ATF?
I don't remember the exact ATF. I don't remember the exact explanation for this. I apologize. I should. So, another solution is to use optical CD measurements. Optical CD measurement, you can say, wow, it's a very bad idea because optics has a very bad. We are dealing now with very long wavelength. However, I'm not showing you. I'm showing it to you. I have some reason I'm showing it to you because first, if you want to understand optical CD measurements, the very simple way is to take a light like a lamp and illuminate your substrate and collect a scattered light and move this or this can be the collector or the illuminator, depends, and move it and plot the light intensity as a function. For example, you can take this structure, illuminate everything, and put here a very, very, very narrow light detector. This is one option. And plot this light intensity versus distance. Now it's a problem because typically the detectors are pretty large because they are supposed to be of the wavelengths of the light. And if you take a visible light, wavelength is like 500 nanometers. However, there are some clever collectors today which are very, very narrow. It's called near field detectors, and we can use them. Second, they're not so repetitive, not so repeatable, limited special resolutions, but they're very cheap. So for example, if you are doing lithography, but it's not nanolithography, you need to measure like 10 microns, 50 microns, optical CD control are available. And OCD measures the fine structures by matching measured optical signal with simulation from a pre-built structure model. So one interesting feature is that you are taking the image with a very wide detector, you generate this image, but now there's, in the last few years, people now developing a complete new family of CD measurements. Using optics, they measure the reflected optical image, but the reflected optical image depends on the line width, because the light hits the substrate and is reflected, and the reflection depends on the fine structure. What you can actually do, you can measure the structure by actually solving the wave equation and the OCD metrology using optical scatterometry with rigorous coupled wave analysis. This is called the RCWA modeling. And this is a very interesting concept, because about, I would say that 10, 15 years ago, people thought this is kind of a, how can you measure 30 nanometer lines with 500 nanometers wavelength? The answer is, today you can measure it. But the measure is not trivial. And I took this from a paper by this interesting paper. What you actually do, you take a laser, for example. By the way, there are few ways to do it. There are few companies that are doing it. There are few features, but the concept is that you illuminate it and measure the scattering, and then try to fit the scattering to a certain model. So you take a periodic structure, illuminate it with a laser, and collect the light. And what you do, for example, one option is you can actually change the position of the laser, change the position of the collector, and or you can, if you can see here, you can also use a polarizer here to use a polarized light, and an analyzer here. Again, the idea is that you can measure the light intensity by using some optical components inside. This is simple scatterometry. This is what we call, if you look at the number, this is the transmission reflectometer, light hitting the substrate, and we get just reflection. Another option, this is B. B is that instead of measuring the light intensity, we measure the polarization. I don't know if you're familiar with a tool called a ellipsometer, but you take the light, you polarize it, you measure the reflected light, and then you analyze it with an analyzer, which means you don't just measure the intensity, but you measure the intensity for the two possible polarization, TE mode and TM mode. So this is called ellipsometer scatterometer. C is it's a diffractometer. Basically, you illuminate it and put here some prism to generate some diffraction. And this paper is a review paper about possible scattering measurements. But the idea is that I want to bring you the concept. The concept that the light hits the surface and we got some reflection. We can measure the light intensity. We can measure it with polarization. We can use a diffractometer to get some diffraction. And the complex model, this is even a new system. You use a combination of ellipsometer and a prism here. Let's look at what we actually measure. So far, I gave you some imaginary or some images of photoresist, but I'm not so much interested in the photoresist. I'm interested in the result of the lithography. So let me show you, and this is the first time that you see a real transistor in this class. This is a transistor here. This is a polysilicon gate. This material is called polysilicon, and we discuss it in the lecture when we discuss chemical vapor deposition. We will discuss how we make this polycrystalline silicon. And after lithography, this photoresist is very, very narrow. Typically, on the side of the photoresist, people put a spacer in oxide, this white stuff. Under it, we have SOI, silicon and insulator, and the source drain here is the silicon germanium. This is very advanced 32 nanometer technology. And I would like to measure the width of the poly after the lithography. This is the real critical dimension measurements. So one option is to use SEM, to take an SEM and use the beam of the SEM to scatter it. The E-beam scatters, I measure the secondary electrons and I get a very nice image. However, SEM imaging, we get problem of charging, and SEM is a very expensive tool and also not so fast. It's actually not so bad, but if I can use optical method, I can accelerate it. Optics, I can run it much faster. So what usually do, you take this structure and you model it. You say the blue part is silicon germanium. Silicon germanium, I know the optical properties. This part is polysilicon, the red one. I know the optical properties very well of this material. They are very well characterized. I know the refractive index, I know the absorption. On the side, I have an oxide. This is called a spacer. I will explain it to you later why we use it, but if you can guess from the name, it's a spacer. I need some space on the sides of the transistor. It's been the actual role of the spacer is to reduce the electric field inside the transistor. I take this structure and I illuminate it with light in my simulator and solve the wave equation. It's a scattering equation. I can assume light is coming here and it's scattered. And I can calculate the scattered light. And this is what you actually do. You actually solve, and this is example, this is a memory structure, and you actually illuminate it and you calculate the amount of light reflected from each one of the components. So I did not give you what is red and what is blue, but this can be low intensity, high intensity, different intensity. So I can simulate what is the reflected light from every position. Then this is simulation. And what I can actually do, for example, I can illuminate it. In this specific one, this is a scattering system where I polarize the light. I illuminate my structure, and this is, for example, this is how it looks. This is my DRAM, and I have the actual DRAM, this is an actual DRAM, and one is the simulated region, one is the real image, and I fit. I measure the scattering versus angle, or the scattering light, and I get a certain picture. From this picture, I fit it to I take the simulation and I fit the two values, and I can calculate, for example, correlation between this the light intensity in one mode, and this is simulation versus measurements. This is the end of the lecture, and this is a very complicated structure, but I will explain to you again just the concept. I'm not giving you the full idea, but this method assumes I have a certain structure, line with spacer, with some other, and I know the exact structure. I illuminate it with light, and I know the scattering. I change the angle here, and I measure the scattering. And I have few methods. I can change the angle as is. I can change the angle and the polarization. I can change the angle and put here another optical element. But for every optical situation, there's a one-to-one relation between this structure and the scattering. And the scattering, I got a picture of scattering versus angle. And for every line width, I will get a different scattering profile. So I solve the wave equation. For example, in this structure, in this paper, they actually solve it for, this is the memory. This is, you see the periodic structure. There's some kind of a memory structure. And they solve the wave equation from here. And by knowing this analytical solution, in this method, I gave it even the name, this is called the rigorous coupled wave analysis. By fitting the scattering to the model, for every line width, I have one pattern in the scattering. So I look at the scattering pattern. From the scattering, I can extract the wavelengths. The line width. Now, this method was initially considered, as I told you a long time ago, as it's nice in the lab, but not so practical in manufacturing. However, now it's in manufacturing, people use it more and more. It's called optical CD measurements. You measure the scattering, and from the scattering you can extract the critical dimension. The advantage, it's faster, it's optical, no charging. It's a much cheaper method, it runs faster. But the proof of the pudding is by eating, and the proof is that actually you can actually get very good measurements, very good correlation between actual measurements. And I apologize for the very poor quality, but I maybe show you some better results later. The problem is not so much data available, but this method is gaining ground recently. So I really would like you to be familiar with it. So this is about, in the last 5 hours, we discussed lithography of all aspects, how we measure the lithography. I gave you a little bit about electron beam metrology, about optical metrology. I did not go into details, just to give you an idea to talk about this optical model here. You really have to be experts in optical, in geometrical optics, in diffractive optics. It's not so trivial to solve these structures, but people are using it. However, what I'm going to give you now is we missed some parts. I didn't tell you about how we actually pattern 32 nanometer technology and what is the next generation lithography. So we finished lecture number 2, which is conventional lithography, conventional optical method, conventional resist method, and a little bit of metrology. And I explained to you E-beam lithography, E-beam metrology, and optical critical dimension control. Next lecture is lecture number 3, which is next generation lithography, immersion lithography, E-beam lithography, X-ray, all the nanolithography, stamping, all the features that people play now. And we start it in the next hour. I'm planning to finish it next week in the first hour, and then we move on to junctions and doping. So the first 2.5 lectures are about lithography. You will have a lot of homeworks, a lot of questions, and I know that it's kind of, we showed you some topics and I didn't go very deep to some of the topics. If you want to know more about it, let me know. We have a lot of material. So we take a break now for 10 more minutes. Okay, next lecture, lecture number 3, next generation lithography, is practically what we hope that we'll do in the next few years. Now, I would like to introduce to you a concept that it's usually taken from other, from the Department of Industrial Engineering. But if you are designing a lithography, one of the issues that you do is design for manufacturing. For example, one of the issues that we are looking at, this curve is what is the, if you remember, one of the problems that we are dealing with lithography is what is the resolution that we get. I plotted here, for example, this is a feature of the photoresist. And this is the photoresist of the normal, this is 65 nanometer photoresist. If I will take a K1, forget about this for a moment. What are the needs between about 10 years ago until now? 10 years ago, we used the technology was at the 880 nanometer. People used excimer laser, krypton fluoride, 248 nanometers. 130, people moved to 193 nanometer. And K1 improved to 0.65, 90 nanometers, 65. K1 0.35, and here we can about now we can assume K1 in the range of 0.35. So these are the needs for the K1. K1 is the factor that we use for the resolution. So how do we get better? But if you look at this value, you can see that we are basically, it's very difficult to get below 0.35 from practical values, no matter what we use. So how do we improve the lithography?
So what are the process and the...
I prefer not to explain the process now. I want to skip this part of the lecture and to move on to something which is, to my opinion, more interesting. How do you get better lithography from what you have? So one very nice approach that people are now using more and more, it's called double patterning, and I'm going to show you what does it mean. This is how you can improve the resolution by a factor of 2 using same conventional tool. So this is a very interesting technique. Or use next generation lithography, or E-beam lithography, X-ray, scanning probe lithography, or soft lithography. So let me teach you first the technique of, I think this image is a little bit not the best quality. Can you see it? Is it in focus, or can you see this? I have to apologize. You can use it when you read it on your screen, but projection in this room is not the best quality. So I will move to this picture, which is actually contain the same information, but in a much clearer way. So this picture you can use as a reference and read it at home, and the same information is here. In a conventional lithography, this is your photoresist, the blue, and this light blue is your whatever you want to etch, and you transfer the image from this photoresist to this substrate, and this is called single exposure. In the single exposure, this is your conventional single exposure, this is your lithography. The limits of lithography define the line widths here, and if you know this structure, you can get this feature. Double exposure is a slightly different process. Let's say this is, you want to define this blue line, and you put on top of it this gray layer, which is just, we call it a hard mask, and on top of it you put the photoresist. And in your photoresist, you do the exposure with this resolution. So this is the resolution of your mask. Compare it to the resolution of the mask here. So the resolution here is much, much more relaxed. So what you do is the following. Next step, you remove the hard mask, the gray material. Then you deposit photoresist again. The next step is expose now with a complementary mask, and here this is illumination, and here is the illumination. But now the pitch, the distance between the illuminated area is the same as here, but we shift it. So now the exposure is here and here. Next step, what we do, we etch the hard mask. Now we remove the photoresist. What do we have? We have a hard mask, the gray material here, here, and here, and here. So the next step is to etch, use the hard mask as the mask for the etching. And then we remove the hard mask. And we end with this light blue material exactly the same as here. So the end of this process is the same as the end of this process. However, here the mask, this was the resolution of the mask, and this was the resolution of the mask here. So I can get the same lithography with a mask with half the resolution, but I need 2 masks. Instead of having 1 mask, I'm using 2 masks. So I pay with a more complex process. I have to do the lithography twice, and I have to make sure that the alignment of the 2 masks is good. However, I can get twice the resolution with the same mask, or same resolution on the wafer with half the resolution on the mask. So this is called double patterning lithography, and there are, this specific one is The challenges are first the photoresist. Second is the overlay. Overlay is I need to do two exposures, exposure 1 and exposure 2, and they have to be well aligned. And design for manufacturing. I need what are the errors? There are also the issue of the computer-aided design. How do I design the mask to do it? Because not always I have lines which are straight. Sometimes I have squares, sometimes I have corners. And how in a complex mask, how I do the double exposure. So the cost of ownership, COO. So COO is cost of ownership. Now, let me 1 minute on COO. COO, cost of ownership. Ownership. Which means you own a machine. This machine costs you money. How much money you invest in buying your machine? Can you guess what is the cost of a normal exposure tool today? Stepper. Cost of a stepper.
50 million.
He was much closer. It's more than $10 million. Can be $50 million. So in this machine you use one exposure. Here you use two exposure per line. So you have to, instead of having one machine, you need two machines to get the same throughput. It means instead of investing $50 million, you invest $100 million, which means it costs you more per wafer, or per step. So it increases the cost of manufacturing. And just for your general knowledge, let's say you want to build a fab. Let's say you want to build a manufacturing site and buy some of these very expensive cameras. You don't need one, you don't need two. You need sometimes in the range of 20 or 30 or 40 cameras. So it costs money to buy the equipment. Now, if you think about how much the capital equipment, we call it capital equipment. Capital equipment is the equipment for manufacturing, is the cameras or the steppers, the developing tools, the pumps, all the equipment. In the next lecture I'm going to teach you about ion implanters. So the total capital equipment, let's say if you build a company, if you build a fab, cost of capital equipment can be more than 60% of the cost of the company. And then you have to build the building. It's a very expensive building. It's also 20-30% of the cost. So most of the cost is in equipment. So this is a problem, because here in double exposure you get very nice lithography, but you increase the cost of manufacturing, you increase your cost of the building, and you have to charge more to cover your costs. So it's a problem. It's a very nice technology, and many people are using it, but you have to. Now, for example, this is a 25 nanometer gate feature using double exposure, arguably two physical limits of CMOS. So basically people show using standard tools. This is source, drain. This is 25 nanometer lithography with a standard tool. This is printed in MIT Lincoln Lab. This is a 0.6 numerical aperture krypton fluoride stepper. The krypton fluoride stepper, this is krypton fluoride stepper. This was used for 180 nanometer technology in the year of 2000. So you can actually, using the double exposure, can maybe use cheaper tools. Again, I don't want to do the economy side of this issue, but you have to understand that technology and economics are going together, and you have to take this into consideration. But the nice is it's a very nice feature. Questions?
Isn't 22 nanometers available today, not commercially, but with standard silicon chips?
I'm going to show you later how to do the 22 nanometers without the double exposure. This is not the only trick we have in the bag. So this is our few others. So, for example, Think about these structures, and there are some electrical engineers in the room, so you can recognize this is a SRAM, static random access memory. So this is SRAM, it's 2 inverters, 1 inverter, second inverter, and the 2 path gates. So the desired layout, this is a 6 transistor SRAM cell. So normally you can have this desired layout. But you can actually think about it, instead of doing it with 1 exposure, you can get the same structure with 2 exposures. And this is actual layout after the first gate patterning, actual layout after active patterning, and actual layout after second. So you can actually, this is what you want in the end. You want the 3 transistors with 2 gates, and this is the pass gates. This is the second half. You can combine the same, instead of having like 1 exposure, you can build it by some 2 different exposures, and you can gain some interesting feature. And by the way, this is what you have on the mask. This is this is how it actually looks. And this is after. This is look at this is what you have, what you want, and this is what you get. Actually, you get some rounding of the structure. Now, single exposure requirements. If you have, this is your lithography, this is the substrate, and you have some photoresist. The photoresist had some errors, so you have a target CD in lithography. This is what I told you before. Your CD, your critical dimension, you define it. This is my value, and I can be plus minus 1%, 2%, depends on the product, depends on the cost that you want to invest in the process, or the cost that your product can work. So you have requirements from the CD of the photoresist, and then you have the target CD from after this is the photoresist. You etch the orange layer, you etch the green layer, and this is what you have at the end. This is your target CD. For example, you can have variations of plus minus 10% CD. You can define it. I took this number from some papers by Sematech. For example, in some specific process, just to give you an example, the requirements were delta CD litho 7%, overlay 20% of CD. This is not magic numbers, just example to give you typical values. Some process are found in some papers which were published. So this is the single exposure requirements. When you do double exposure, you have more requirements, because now you have twice the exposure. First you define this feature. So in the first exposure you define this feature. You remove the photoresist and you put another photoresist and define the second feature, and then you can, this is the end result. So you can double the resolution. But now, if you want the CD to be less than 10%, your litho requirements become 3.5%, and your overlay requirements become less than 7%. So in a conventional lithography, if you want 10% target CD, this will be the delta CD for the litho and the overlay. Now in a double exposure, you gain with the resolution, but your process control should be much tighter, because now you are less tolerable to error. So this is what you pay. Nothing comes free. Give you an example. This is images. This is double line patterning of 32 nanometer half pitch flash memory. And this is the test structure of the flash. This is not the actual area. This is one pattern in the flash memory, in this specific flash. You take the mask. It was supposed to be 64 nanometer. You break it into 2 masks. And this was done in a tool by a company called ASML. And they published it in their website. And this is what you get in the end. This is the very nice resolution. This is the poly patterning. This is an annular image, and with a 1923 nanometer wavelength. And look at the numerical aperture, 1.2. And you can ask me, how can I get and I have 1.2. Because we all know that numerical aperture is a refractive index tam sinus theta. Theta is the opening of my optics. If I want to get sinus can be larger than 1. I have to do immersion lithography. This done with immersion lithography. So lithography challenges, again, courtesy of Intel that published, this was published in a conference a few years ago. If I want to work with I-line 365 nanometer, this was 1990, resolution was like 0.35, 0.5. Krypton fluoride lasers allow a resolution of 130 nanometer. 193 nanometer allow going to 65 nanometer. Next, going from 193 nanometer to really short wavelength, and I'm going to show you today about these two. And this is just to show you, this is how it looks. This is the actual lithography of some pattern published in Intel in their publication. I think it was one of the conferences in 2006. This is how the actual lithography look of this specific structure. So 193 litho will continue to dominate the next 5+ years. This was written in 2006, so we still have 1 or 2 more years. But it's actually going well. And the key is immersion lithography, to use liquids and double patterning, and or to move to something else. We call it NGL, and I'm going to show you about what is the something else. If we are optimistic, 2012 is ready for the EUV 30 nanometer. Let's see. We have 2 more years to wait, and it's a very, very strong effort to bring it to manufacturing. But now before we go into the technology, I want to give you a little bit another aspect of lithography, and this is the aspect of yield. Yield means how many good wafers you get. What is the percentage of good wafers that you get from your wafer? 100% yield means every single die that you make is working. It is working according to the specifications. Now, you never get 100% because you have a lot of random defects. So this is technology node. This is 350, 250, 180, 130, 90 nanometer. So if you talk about random defects, when the technology was 350 nanometers, about more than 15 years ago, then it was a little bit. Now you lose because of defect density, but you also lose because of lithography-based yield. Problems which are during the lithography process. Some variations, some defects, some problems with the lithography, because the lithography itself has some random properties. And you have the systematic defect, and also you have process variations. And this, it's called like design-based yield. It's and you can see that if you this is again if you work for this specific process, and this is for a given specific process, if you use the process of 350 nanometer to produce, or similar technology to produce a 90 nanometer, you get like 50% yield, which is unbearable. So people are changing the process and improving. So this is, but ignore a little bit the numbers. The problem in your manufacturing are random defects and lithography problems, and process variations. Because of this, you lose yield. And you are basically reaching the critical area, and you are solving it. You are solving it by improving your process. For example, you're improving your lithography. You are planarizing the substrate. Instead of working with to be out of focus, you planarize it, and I'm going to give you a complete lecture how you planarize. You planarize using a technology called CMP, chemical mechanical polishing. You literally take your wafer and polish it. And by doing this, you improve the process variations. And the question is how to do the 32-22 nanometer technology. Now, it's assumed that 193 nanometer lithography will stay for quite a while. Listen, when you pay more than $10 million for a camera, you don't throw it away every 2 years. Yes, some companies can do, but listen, you extend it 1 year, you can gain a lot of money. Double patterning seems to be going strong. Stitching means when you take two patterns and stitch them together. Layout decomposition, you look for 3D effects, and I'm going to talk again about UV lithography, so let's skip to the next one. I'm going to talk about immersion lithography. I'm going to talk about optical proximity correction, phase shift mask, off-axis illumination, resist trimming, and double exposure. So what we already studied a little bit about phase shift masks, which means instead of using regular mask, I'm using a mask with some phase shifting. This is an improvement. I can do off-axis illumination. Instead of illuminating in perpendicular light, I'm illuminating the mask in an angle, so I gain some information. Resist trimming I did not explain. I will going to explain to you immersion lithography. And optical proximity correction I give you a little bit when we discussed masks. So this is your design pattern. Now, one option is I can take the image of this mask and make the mask and take the exposure and everything will go well, but I will have some resolution limits. So another option is to take a mask which is pixelated. Instead, taking the regular mask, divide it into pixels, and for every pixel to change either to use optical proximity corrections or phase shift the mask. And this is the result. Is much, much better. So I'm not sure if I have another I should remind you what is the phase shift mask. Phase shift mask is a mask which I can change the phases in certain positions to improve the image. Ideally, you can take the mask, and every pixel on the mask you can design the transmission and the phase to generate a better image as a result. This is kind of an ideal structure that people might use it in the future. So lithography system price evolution. This is the answer to, this looks more like a class in economy, but lithography and economy are going together. Because lithography is the most expensive part. I mean, the other equipment is not cheap also, but the section of lithography is the most important and most expensive section. So if you go in 2090, a stepper cost in the range of 2 million euros. This is in euros. So, yeah, but by the way, it's a little bit misleading because at that time the euro was like 80 cents, which is now the opposite. So this is in dollars, it was even more expensive. And if you take this interesting feature, they took all the tools existed in the market and put their cost in a log scale in the cost versus year in a linear scale. So this is I-line, 365 nanometer, krypton fluoride, 248 nanometers, argon fluoride, 193, and EUV, 30 nanometer. And this is the costs in a log lean scale. Surprisingly, it's a straight line. This is one very strange or very interesting feature of Moore's law, that everything, every change, the dimensions, density, everything when you plot on a scale which is log versus lean, log the feature versus linear time, you get a straight line. And we are about now. So it's not cheap. So how do you... Now let's talk about next generation lithography. To understand next generation lithography, we have to... I would like to bring to your attention some very useful source of information. The ITRS. International Technology Roadmap of Semiconductors. So you can, if you Google it, there's a website with all this information, and some of the information I took from this website. Another very interesting website is the website of Sematech. Sematech is an organization with few centers in the United States and also in Europe, which deals with next generation technology. It's a kind of a research center where companies and universities are working together about future technologies. So one of the results of the ITRS is a lot of information of what will be the future. For example, this is the year 2001 to until 2016. So until here, this is fact. We know. 11 and above, this is a guess. So 10 years ago, 2001, technology node was 130. It was 90 in 2004, 65 2007, 45 today. You can argue there are some other technologies like 38, but allow me, I cannot put all the information on one graph. So today is approximately leading edge is 45 or slightly better. 2013 it will be 32. 2016 it will be 22, hopefully. But this is a forecast, so it can change. So if you look at DRAM half pitch was 130 here, 90 here. So the DRAM half pitch is about the technology node. The MPU microprocessor, when the node was 130 nanometer, microprocessor gate in the resist was 90 and the post edge was 65 nanometers. So because the pitch was 130, the gate was 65. So, and if you look at the number here, at 45 nanometer node, the gate width was 18 nanometers. This is post edge. Doesn't mean this is the electrical length of the device. This is the gate in the resist. It was 25 nanometer. So we are dealing here with, this is nanotechnology. And this is done by optical lithography. But what kind? So the critical layer exposure method, here it was krypton fluoride 248 nanometer. Then it became argon fluoride with some work, and I will explain to you a little about EPL, electron projection lithography. Electron projection lithography is using electrons, but not a single beam, but like an image. This is an effort, a technology called scalpel, which I'm going to show you a little bit about it. Very interesting technology, still under research. You have the fluorine lasers at 157 nanometer immersion, and hopefully the EUV. So we are here, you can see we are in a transition period now. EUV or F2 laser or EPL, one of them will win. But we have the argon fluoride lasers as a working course. So immersion lithography. Immersion lithography is a lithography where you take your optics. This is your projection optic. The mask is here somewhere. This is your projection optic. This is the wafer, stage, sorry. This is the wafer. On the wafer we have some photoresist. But here we have this blue. We have liquid supply here, liquid recovery here. We flow liquid in this region. Now it's very interesting because we have, if this is the lens, we have liquid only in one side of the lens. On this side of the lens, it's air or vacuum. So we have a little bit, it's a kind of interesting optics. We have to change the equations, but for the resolution we don't need to change the equation, because for the resolution we care about how we collect the light from the image. So the resolution equal K1 lambda over numerical aperture, and numerical aperture is n sinus theta, and we got the resolution is K1 lambda over n times n sinus theta. So basically we improve the resolution by a factor of n. And the reason is we basically collect now the light from a wider angle on the bottom. But interesting enough, the depth of focus, this equation, be careful when you calculate depth of focus. Because in a classical system, when we have air on the top and air at the bottom, the equation was K2 lambda over n numerical aperture square. But now, if you want to calculate the depth of focus for immersion lithography, you cannot just take this equation. Because here we have liquid in the bottom and air on the top. So we have to be more careful when you calculate. And we have to go to the fundamental basic, and Asya will explain to you a little bit in the lecture. But let me give you, I'm not giving you the full calculation, but let me give you about what exactly is depth of focus. If this is your lens, and this is your image, this is your primary beam hitting, and there's another beam of the same picture hitting the sides, and if this beam and this beam come from the same place, they should meet in the same place. And they meet in such a way that this beam and this beam, when they meet on the wafer, they are in phase. This is how you generate an image. Basically, the image is spread, and for every pixel you collect it, and they all meet, and they are exactly in phase here, and then you build the image. Now, let's say I move the wafer up. Now this wave propagating here, this wave now propagating, and now we generate the image here. This and this are not necessarily in phase. So I destroyed the image. But I can say that I'm in focus if the phase difference here is less, for example, like pi over 4 or pi over 2. If the change in phase between here and here, this beam and this beam are exactly in phase. If now this move up, the phase change here, the phase change here, but if the change in phase is not so much, I can say that I'm still in focus. So if you calculate this, you can calculate the equation for the depth of focus. And the equation is depth of focus is some constant, lambda over n, 1 over 2, 1 minus cosinus theta. We'll give you the exact calculation. Actually, the exact calculation appears in one of the slides in the second lecture. But you can do it yourself. You know this distance, you know this distance, you know the optical distance. Calculate the difference. This is very simple. The triangle, you know from here to here we are in phase. Calculate the change in distance as a function of this distance. And you say, this is depth of focus when the change of phase is pi over 2 or pi over 4. I don't remember the exact value. So this defines the depth of focus. So if you do this, you find out that the depth of focus in immersion lithography is K2, which is also about 0.5 or slightly better, times n over lambda over numerical aperture square. So we actually improve the depth of focus. So we improve the depth of focus, and if you think about it, we actually improve the resolution and improve the depth of focus, which is actually, it looks like needs some further explanation, but you have to understand, in a normal analysis you assume that air is in the top and the bottom. Here we have air on the top of the lens and water or liquid on the bottom. So it's, in this situation, the resolution improves because we have to keep the same numerical aperture, but the depth of focus also improves Because now, instead of, when you put your liquid, you got the collection angle is much wider now. So if you put here the lens, you can allow further increase or decrease of the wafer. So the actual depth of focus actually improves. So the nice thing about immersion lithography, you improve the resolution and also improve the depth of focus. Now, so you extend the lithography. If you think about it, this is your wafer, and you take your this is your lens. This is your wafer. If you want to use immersion lithography, you have to design your optics that the bottom should be relatively flat. You cannot make a curved lens at the bottom. You need to design your optical system to be flat at the bottom. You can put a liquid, so you can actually convert existing lengths and resolution remain the same and increase depth of focus. Because if you convert the existing lens, basically the numerical aperture remains the same. Or develop a new lens with a higher numerical aperture. But then you pay with resolution. For example, for argon fluoride, the fluid is typically water. With F2 fluid, the index must be bigger than 1.5, otherwise continue. There's no argon fluoride, to remind you, is 193 nanometer. Fluoride is 157, but it's very expensive and it's very slow. So in order to get improvement and to use F2 lasers, people have to define or invent an optics with numerical aperture more than 1.5 to make it cost effective. You don't want to invest a lot in a new technology which will be almost the same as the old technology. So this is a question now. So average advantage of immersion lithography, like in argon fluoride dry, F2 dry, medium here is air. Here you need to, with fluorine laser, you need N2. You cannot just use regular air. N is equal 1. Lambda over N here is 193, 157, because N is equal 1. And you improve by a factor of 0.81. Argon fluoride immersion in water, N is 1.44. And F2 immersion, people don't use water, use an organic fluid, is a PFP, is some kind of organic liquid. But here N is 1.37. So this you gain only if argon fluoride is, you improve the resolution to be 0.7 or 0.69 of this resolution. This is what you get with F2 immersion. So the other issue is to look at the depth of focus trend. The 2010 depth of focus of the system today is in the range of between 100 to 200 nanometers. This is practical numbers. Let's say, with all due respect to the equations, those are the practical numbers. But you can see that along the years, the depth of focus is going down. The improvement, hopefully, if this is depth of focus, this is the circles are depth of focus for the 193 regular one, this is 193 wet. So the main advantage actually for using wet lithography or immersion lithography is increasing the depth of focus, while in the same time, hopefully you can get better resolution, or same resolution with better depth of focus. You can actually plot the depth of focus versus resolution. This is basically even the advantage of immersion lithography is even more. It's clear. This is depth of focus from the good old days of actually this is from 438 nanometers, which was early 90s. So this, what you see here, is a graph of almost 20 years of lithography. So this is the I line, this is the G line, this is the XML lasers. And when the resolution was 100 nanometer, the depth of focus was about 300 nanometers. This is wet. wet lithography or immersion lithography, you can get the same resolution but much better depth of focus, or with the same depth of focus, much better resolution. This is practically what you gain. Now, tools. Just to show you some tools, I picked these pictures from the website of Sematech. They have some very nice presentations there. Optical lithography tools. You take a regular optics, put some integrated liquid supplies, temperature controller, degassing to remove some air. You have to understand that inside liquids you can have some dissolved air, dissolved nitrogen, dissolved oxygen, and if you pass light through it, you can generate bubbles, and bubbles are a problem. So this is an image of the typical platform. This is another immersion lithography tool. This is from another company, and you see here, this is the stage, this is the wafer, this is the supply of the liquids, and this is the optics. This is another immersion tool. Basically, I picked up from the website, very nice website, as everybody published their very recent tool. But the idea basically is you have the lens, the mask, and you put it in liquid, and typically you flow the liquid. This is actually the image of the lens. This is a high numerical aperture lens. It's a pretty big lens. I don't have here a scale, but it's a pretty big lens. This is how it actually looks, and this is a 0.85 it's a lens with a 0.85 numerical aperture. I don't know exactly the cost of it, but it's not cheap. It's nice. We get very theoretically, immersion lithography works nice. Problem is bubbles and polarization. If you have a feature, this is your wafer, this is your exposure area, this is your lens, you have water flowing. If you have bubbles, the bubbles can cause some defects. The question is how to avoid formation of bubbles, so people developing methods to avoid bubbles. This is how it looks. This is if somehow you have a bubble in the liquid, this is a printed pattern, and you can also have particles. This is a fall of particle. I think I showed you some of these images in a few lectures before. This is a printed bubble. This is actually when the bubble is in the image, and this is a stain after you dry the wafer. Now, if you have a lens and you illuminate it with a polarized light, this is what I call a TM, and this is the electric field. The magnetic field is transversal, it's perpendicular to the, is parallel to the lens, and this is the TE. And what you actually have is so far neglected the effect of polarization. I assume that we don't care. In a regular lithography, it has some effect, but it's not so significant. But if you have a light, and you can have TE polarization or TM polarization, you have to remember that the light is going through the mask, and the mask has some metallic components. So if you have a TE polarization, it's going through the mask, through your wafer, and hits the bottom. The bottom, we have an electric field in in the TE, and the electric field here is in parallel to the wafer. If you have a TM polarization, the electric field is not in parallel to the wafer. It comes with some angle. But what we found out, if you do the actual modeling, that if we have TE polarization, you have better contrast than TM polarization. This is after you do the exact modeling. The TE vector, you get much better contrast. Not much, but you get better contrast. Yes.
Don't you need also to take it into consideration when you use wet lithography? Because water...
When you use, absolutely, when you use immersion lithography, this effect is even more pronounced. Absolutely. Because of the high refractive index.
Different end for magnetic and electric?
Yes. So actually, it's a very good comment. this effect of polarization, when you do immersion lithography, is more pronounced because of the refractive index of the water and the effect that the actual electric field, when it hits the substrate. And there's other issues that I did not discuss. Typically, we assume that we hit the substrate, we hit the photoresist, which is a dielectric. But under the photoresist, we have also, if we remember, the anti-reflective coating. So we have to take this into consideration in the modeling, and this is the result. The result is TE give better contrast than TM. So one of the things you can imagine that you may want to have design your system with an illuminator which is polarized. This is another. So far I neglected the mask. The mask, I say this is a piece of glass with metal. Not exactly correct. It's a piece of glass with metal, but this is the glass, or reticle it's called. And typically on the glass we put a very thin membrane. We call it a pellicle or hard pellicle. Typical thickness of glass is few millimeters. This specific one is, it depends on the size of the mask, but this was 635 millimeter, and about less than 5 millimeter of it people put a pellicle. This is a membrane, and the reason is, if by some accident we have a particle on the wafer, if the particle is on the wafer, we print the particles. So every die will be defected. So the yield will be 0. However, if you put here this membrane, this polymer, this very transparent thing of polymer, if the particle is here, it is not printed because it's out of focus. If the particle is small enough, the image of the particle is not on the wafer, it's somewhere else. So we don't get the image of the particle, it's out of focus. So this makes the masks much, much less sensitive to defects. So this is called a pellicle.
Can you explain again?
Sure. This is my mask. And on the mask I have a feature. Let's say, and another feature. And I illuminate it. I have here the optics. And this is my wafer. I get the image of the structure, and if I'm in focus, I get the same feature here reduced, and everything is fine. Let's say now, for some reason, I have here a defect, some particle, a dust particle. On every feature, I will get this dust particle. So it will ruin my day, basically. So the yield will go to 0. So what you do, you put here, under the wafer, a thin membrane of polymer. It's called a pellicle. It's actually a sheet of plastic, of some polymeric material, which is transparent. So now, if there's a defect here, or a little particle here, the image of this particle is through this optics. But if the focus of the mask is here, this little particle, the focus will be somewhere else. So on the substrate, the image will be diffused. So the intensity is much lower, so we don't print it. So this is called pellicle. But we have to be careful how we make the pellicle. It's actually very... I'm showing it to you. We don't use it in the university, because in university, as I told you, we can live with it. Yes. But if you do in manufacturing, you need to do it. This pellicle, it's a lot of science in how do you make the right pellicle, what material to use it, how to make it to withstand the long process, how to replace it if needed. So it's all the practical issues. But this is how I wanted to show you by the end of the lecture. This is how a real mask looks like. This is a real mask. And if we talk about, if we can end the lecture about the economy of lithography, the cost of mask is also going exponentially with time. So not only they become cheaper, they become more complicated with pellicles, more features. If we do double lithography, we need twice the masks. So the mask become a good part of the process, and they're not cheap. A good set of masks can cost a few $100,000. So see you next week, and we talk about EUV.